Hello, and welcome to a little video about Target 3A, recognizing functions and function families. All right, a relation is the mapping or the relationship between a set of inputs and a set of outputs. Now, relations can be modeled in several different ways. It can be modeled through ordered pairs, as you can see there, an equation. We can have a verbal relation, so a sentence in English. The relation between students in your school and each student's birthday, right? That's a relationship. There's mapping, as you can see, the two circles with the arrows. There's graphing, standard graph, XY grid, and there's tables. So all 1, 2, 3, 4, 5, 6 ways are ways to represent relations. Now, functions are special kinds of relations. Functions are relations that assign one domain, which is an x, exactly to one value of the range, which is the y. And it can be represented in many ways. Now, I like to think of it as x and y having a monogamous relationship. X's cannot cheat on their y's. An x, so a domain, should only be with one y. So let's see. So that's what makes it a function. All right, number 1. Analyze the table. Is it a function? Well, let's see. Each domain is different. Each domain has just one type of range. Now, it's okay if you see the domain here, this 5 has a negative 5 and the 6 has a negative 5. Because, sometimes different people will date the same person. That's okay. At different times, obviously. If we're going with these monogamous relationship analogy. So, the table, yes, it's a function. Yes, because the domain doesn't repeat. Number 2, what about the map? Ooh, the map is not a function. Check it out. The domain of 4 is cheating. It's going to 5 and negative 5. So no, because 4 goes to 2 ranges, and that is not allowed. 3, analyze the relation by the ordered pairs. There they are. Let's see if this is a function or not. Let's check out all the x's. Are they all different? No, look at that. There's 3's. 2 of the 3's are dating 2 different people. That is not okay. We are cheating there. So no. There are 2. No, let's write that as a word. There are 2 3's in the x's. That's a big no-no. And lastly, let's look at the verbal representation. What do we have here? Students and each student's birthday. Okay, yeah, that's a function because a student only has one birthday. They're only born on one day. Yes. A person can only have one birthday. Okay. Cool. All right. Oops, I don't know if you can hear the bell, but it's ringing on my end. All right, so functions. Functions, I'm going to be using my handwriting, but we're going to be writing this down. So functions are relations, but not all relations are functions. Okay, so every function is a relation, but not every relation is a function. Okay, function notation. So function notation is just another way we represent that something is a function. So if we have an equation and we want to say, hey, this equation is a function without having someone figure it out, what we use is function notation. It looks like this, f with an x in parentheses. it's read as f of x. And it could actually be any letter. It could be g of x, y of x, well, probably not y, h of x, z of x. Any letter of x would work here. Now, the independent variable x is the input, and f of x, your y, is the output. So let's see. Given the function f of x equals 4 minus 6, evaluate f of 3. Now, if there's a 3 inside the parentheses, it means we're replacing the x with 3 in both places. So let's do that. So instead of f of x, I have f of 3 equals, excuse me, 4 times 3 minus 6. Now what you'll do is you'll enter just this part into your calculator, and you should get an answer of 6. Number 6, let's do the same thing. We have g of x equals 2 to the power of x plus 3, and we want to evaluate g of 4. That means wherever we see an x, we put a 4. So g of 4 equals 2 to the power of 4 plus 3. Again, this goes straight into your calculator, and we get 19. The domain is the set of all independent values. Those are our x values. I don't know what I meant to do with this table, sorry. Range is the set of dependent values, which are the y's. Now, why do the y's depend on the x's? Well, because we plug the x in and we get an answer of y. So, depending on which x gets plugged in, we get a specific y. All right. When stating the domain and range of ordered pairs, we list them smallest to largest and don't repeat values. So let's do that for 7, 8, and 9. So for 7, the domain in order of smallest to largest, that's your x's. Let's label that with orange. We're going to have 0, 2, 4, 6, and 8. For my range, which is f of x, I'm going to list my numbers again in order from smallest to largest, 5, 6, 7, 8. 4, 5, 6, 7, 8. Let's do the same thing for number 8. We got our domain, that's our x's. 0, 1, 2, 4. I know there's 2 1s, but we're not going to repeat them. For our range, that's our f of x. We have 1, 2, 3, 4, and 5. Number 9 is the same thing, except instead of having a table, we just have ordered pairs. Remember that our domain is all of our x's. And our range will be all of our y's. Again, in order from smallest to largest. So let's do that. Ooh, range, let's think about that. That starts with -2. There we go. Beautiful. Okay, there are the domain and range for these relations. Now, when we have anything other than like a table, sorry, hold on. The bell's ringing again. All right, if we have anything other than like a table or ordered pairs or a map, we need to think about our domain and range in interval notation, because it's not just these specific numbers. They're going to be numbers like from 0 to 100 or something like that. So let's take a look at what that means. We're going to use interval notation using inequalities. The previous examples of domain and range were called discrete. That's the official name. So it's a list of separate inputs and outputs. But on graphs and equations, we have continuous domains and ranges, meaning it's not just whole 1, whole 2, whole 3. It's 1.1, 1.2, 1.3, like everything in between 1, 2, and 3, like anything in between the numbers. So we need special notation. Now, when we look at a graph, Sometimes we'll have a closed circle, sometimes we'll have an open circle. A closed circle will have a less than or equal to or greater than or equal to, one or the other. An open circle will have a less than or a greater than. Now, how do we know which one to use? The smallest one always goes on the left and the largest on the right. And depending on the circle with that number, we choose either a or equal to or a without an or equal to. So let's, whoops, well that got a little messed up, but that's okay. Let's write interval notation for A, B, C, and D. I think I can fit it up here. Okay, A. A has one circle at 1 and another one at 7. Now both of them are closed, so we're going to make them or equal to's. X is in the middle. Your inequalities should be pointing to the left because X wants to be on the bigger end of 1 but on the smaller end of 7. Letter B. We have a -6 on the left and a 0 on the right. X is in the middle, and we're going to make sure our symbols face the left, and only the 6 gets a line underneath it because it's a closed circle. Now letter C is different because there's no end here. It's just an arrow. Arrows mean infinities. Now, this is going to the left. The numbers are getting smaller and smaller until the end of time. So that means it's negative infinity. Closed circle on X, -2. You can also just write this as X is less than or equal to -2. Because this part doesn't quite make sense. You can't be greater than or equal to infinity because infinity technically never stops. Letter D, similar idea. The smallest number on the left we have is a 2, open circle, X, and our arrow goes all the way to the right. Now, we can still say that it's less than infinity or less than or equal to infinity, but we really don't need to. We can just say that 2 is less than X or that X is less than -2 for letter C. Okay? Number 11, let's identify the domain and range. Okay, the domain is about our X's, the range is about our Y's. Let's see. The smallest X I see here is -1. And the largest X is 4. Let's do the range now. The lowest Y I see is -2, and the tallest is 3. Oh, I forgot to do my dots for the X's. No, with the black marker. Boop, 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 boop. Beep, 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 beep. Perfect. All right. Let's write the intervals of increasing, decreasing, and constant. Now, how do we figure that out? Now, what I like to do is I will put my pencil on the left side of the graph, and I will just trace. So I'm going to trace until my finger changes direction or there's like a turn. So there, I stop because it's going to become flat. But what was happening as I was going left to right? It looked like I was going down. That means we're decreasing. Now, because I'm going left to right, I'm going to use the X's because that's what goes left to right on our graphs. So it's decreasing from -1 all the way to, what's this X right here? 1. Okay. I'm going to choose a different color, and we're going to continue down the path left to right. Now, I'm going to start where I ended, and I'm going to keep going until there's a change in direction. I'm going to stop right there. Now, it's flat. When it's flat, that means it's constant. It's constant from 1 all the way to 3. Now, let's continue. From that same spot, it looks like I'm dragging my pencil down. Once again, that's decreasing. It's decreasing from 3 all the way to the end, which is 4. Let's do the same thing for number 12. Domain is our x's, range is our y's. It looks like I have all closed circles, so I'm just going to go ahead and put in my symbols. Oh, no, I was going to do y's in a different color. Silly Gumin. Okay. All right, x's. Let's go left and right. Our graph on the left starts here. That's -7. And it ends right here. That's 6. For the y's, the lowest the y's go is -2, and the tallest is 8. Now let's write some intervals. Again, I'm going left to right, and I'm going to stop and write down the intervals each time I change directions. All right, I'm going to start here, and I'm going to go, go, go. Oop, I'm stopping. That was flat, so I'm going to call that constant. And it started at -7 on the x's and ends at -4. Cool. Let's continue. Now it looks like here I'm going uphill. Uphill is increasing. I for increasing. Well, it starts at -4. And where does it end? Ooh, at 1. Okay. And then I'm going to continue, and it looks like I'm going downhill. So I'm going to use a different color. Downhill. That's decreasing. And it looks like we're decreasing from that x equals 1 all the way to the end where x is 6. Fantastic. 13, same thing. Let's identify domain. Wow, there's a lot of intervals here, but we can do this. All right. Domain is about our x's, and range is about our y's. All right. So on the left here, 5, 6, 7, so that's -7. Ooh, open circle. I got to change my symbol. -7. And it looks like on the right, I never end. There's an arrow. That means it's infinity. Or we could just say that x is greater than -7. This is probably the more right way of doing it. You could also, you can go as far as to flip it to say that x is greater than -7 that way. All right, range. The shortest part of the lowest part of my graph is at -5, and it's colored in, so closed circle. And it looks like there's no top also because we're going on for forever. So infinity. Or of course you can say that -5 is less than or equal to y, or you can flip-flop it, y is greater than or equal to -5. Either way you do it would be correct. Now let's do some intervals. All right, starting left to right. Okay, it stops right there, right? Because there's going to be a turn. So that was going down, so it's decreasing. And it's from -7, open circle, so no line underneath. And where do I end? Ooh, -5. All right, next. Next, it looks like I'm going up, 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 up. I'm going to stop there. That would be increasing. So it starts at -5, but where does it end? -2. Onwards we go. I'm going to keep tracing until there's a change. Stopping there. So that's constant. Let's write it right here. C4. No, here would be fine. I changed my mind. C for constant. And it goes from -2 on the x's where we stopped. Where do we end, though? 4. And then we have one more interval, and that's just up for forever. That's increasing again. So, from 4 until infinity, or of course you could just say, you know, you could just not include the infinity. You can say x is greater than or equal to 4 this way. Either way works for me. That looks like 43. Let's try writing that again because that was awful. There we go. All right. Onwards we go for just a few more problems, right? We're just going to identify whether or not they're functions. Let's do this. So, 14. Is it a function? Let's look at the domain. Do you see it? I see it. No. Letter B. Let's check out all the x's. Are they all different? Yes. Letter C. Check the domain. Are they all different? No, the 3 is cheating. Shame. Shame. Letter D. This is a tough one. Now, the way I can tell that this is not a function is because this x right here could either be at this y or this y, so no. Letter E. It looks like each x goes directly with each y. It doesn't look like there's any overlap, so I'll say yes. Letter F, look at the x's. Make sure we don't have any repeating. We do. The 2 is cheating. Shame. Not a function. Onwards we go. Now, on the graph, I was showing you with kind of dots, but there is a way to figure out whether or not a graph is a function or not, and it's the vertical line test. On a graph, you can do a vertical line test where your vertical line crosses oh my God, I can't read. If your vertical line crosses 2 or more points at the same x-coordinate, it is not a function. So A, let's draw a vertical line through A. Several. Does it ever cross more than once? Nope. So it's a function. Same thing for letter B. Let's draw some lines. It looks like both of them cross twice. Letter C, again, only once. All right, last problem for number 16. Let's determine if they're functions and decide why. All right, 16A. I can already tell. Check it out, the 3 is cheating. So, not a function. No. 3 has 2 arrows. It's cheating. Letter B. Is this a function? Does every point just have one x, one y? Looks like it. Yes. Each point has one x and one y. Beautiful. Letter C, take a look at the x's. Do they repeat? Because that's what would make it not a function. They don't repeat. Awesome. So yes, x's don't repeat. All right, letter D. Check them out. Make sure no one's cheating. No one's cheating. So I would say yes. All numbers have only one arrow leaving. Right? So no one's cheating. And again, it's okay that 4 and 5 both go to 8 because 2 people can date the same person at different times. You just can't date 2 people at the same time in our monogamous relationship here. All right, letter E. For every house, there's only one and only one street address. Is that a function? Yes. Otherwise, it would make it really hard to mail stuff. One address per one house. Now, you might be thinking, Gumin, what about apartment buildings? Well, in apartment buildings, there's still only one address for that house. You just separate it based on apartments. It would still be 123 Home Lane, apartment B. 123 Home Lane, apartment C. So still one address for each house. They just separate it to make it easier for the mail. All right. If you have any questions, please make sure to let me know or ask your teacher. Otherwise, have a wonderful rest of whatever day it is for you. Bye!